Welcome back. Okay, so now we're going to work out a couple examples of conservation momentum. So let's look at this one. A boxcar traveling at 10 meters per second approaches a string of 4 identical boxcars sitting stationary on a track. The moving boxcar collides and links with the stationary cars, and the 5 move off together along the track. What is the final speed of the 5 cars? Immediately after the collision, you may take the mass of each car to be 18,537 kilograms. Okay, let's go. So, it's always good to draw a picture. If you're not in the habit, which I can't imagine, but if you're not in the habit of not drawing pictures, it's good to get into the habit. So, initially we have one boxcar moving at 10 meters per second. And the mass of the car is 18,537 kilograms. And then finally, they're all hooked together, so you have all 5 boxcars together. And they're all going to, we want to find this final speed. If we include everything that bumps in our system, remember that momentum initial is going to be equal to momentum final. And recall that initial momentum is mv. P is equal to mv.
Right?
So let's call this boxcar A, and then we'll call all this together B. So we have the initial momentum for A plus the initial momentum for B, so this is all initial, equals the final momentum of A and B together, because they're all together. So, you have to think. We have the initial momentum for B, since these are at rest, since P equals mv, the initial momentum for B is 0. So it's all A. So we have the mass of the boxcar times the velocity initial plus 0 equals, in the final momentum, you can have 1, 2, 3, 4, 5 boxcars. So it's 5m times Vf. Now if we look, the m's cancel out, so it didn't even really matter what the mass was, which is nice. So initial velocity is 10. We can finally plug in the numbers, equals 5 Vf. So Vf is 2 meters per second. See? Not bad. Oops. Okay. So now, let's go to another one. So an astronaut is motionless in outer space, and upon command, the propulsion unit strapped to his back ejects some gas with a velocity of 32 meters per second, and the astronaut recoils with a velocity of 0.3 meters per second backwards. That's what the negative tells you. After the gas is ejected, the mass of the astronaut is 160 kilograms. What is the mass of the ejected gas? So again, first thing you want to do is draw a picture of what's going on. So here's the astronaut, and then at the end, the astronaut is flying off in one direction and the gas is going in the other direction. Okay, so everything in our system is the astronaut and the gas. So P initial, this is conservation of energy or conservation momentum. Well, it's an explosion, so it would be momentum, not energy. So P initial 0, everything's stationary. P final is the mass of the astronaut times the velocity of the astronaut. Now notice this is a vector, so we must include the negative. The negative tells us direction, and it's very important. Plus the mass of the gas times the velocity of the gas. So P initial equals P final, conservation momentum right here. P initial 0, P final was P final of the astronaut, and P final of the gas, plus. And again, this negative tells us direction, and this is very, very important. So you solve for this mass of the gas, and you get 1.5 kilograms. That's a lot of gas. Okay, so momentum is conserved during collision. What does this mean? It means that the total momentum of the system adds up to 0 before and after the collision, or does it mean that the total momentum of the system stays the same before and after the collision? Which one is it? I hope you said the second. Okay, so one more example. We have, this is our first example that we did. Now what if the first car bounces? So now we have the first car, and instead of being hooked up with these cars, it bounces off. So why don't you pause the video for a moment, see if you could solve it by yourself, and then restart it and see how you're doing. Welcome back. Let's solve for this. So everything in our system is this first car and these next cars. We'll call them A, and we'll call all these cars together B. So momentum initial equals momentum final. So P initial is P initial of A plus P initial of B initial, and the momentum final is P final of A plus P final of B. So notice we kept these separate this time because they're not hooked up together anymore. Okay, make this a P. So initially, these aren't moving, these cars aren't moving, so this would be a 0. Okay, so we have the mass of A times the velocity of A initial equals mass of A times velocity of A final plus mass of B times velocity of B final. I'm going to go over here. So we'll just call the mass M. Velocity of A is 10 plus, or equals, sorry. Mass of A is still M times -1. Remember, the negative tells us direction. Plus, and then we have 4 cars, so it would be 4M times VF. And we solve for VF. Well, there's an M in every single turn, so we could divide that out. 10 minus 1 equals 10 equals -1 plus 4VF. 11 equals 4VF, so 11/4 meters per second equals VF, which is a little bit bigger than 2, which we got before, which makes sense. When things rebound, they tend to go faster forward. Okay, so did you get it? I hope you got it. Okay, so that is that example, and we'll work out more later.